Let's look at a few problems associated with force and motion. A 35 Newton block, so that is the weight of this block, slides down a plane as shown. So the motion of this block along the plane is downward. Its acceleration, however, is in the upward direction with a magnitude of 0.7 meter per second squared. Find the coefficient of kinetic friction between the block and the plane. Of course, the step number 1 is to sketch the free body diagram that outlines all the forces acting on this block. So let's start with the simplest, the weight. Weight is always vertically downward, and the magnitude of the weight is given as 35 newtons. And then you have normal force that acts 90 degrees to the surface of the plane. So normal force acts from the plane to the block in the direction shown. Since the block is moving, there must be kinetic friction involved in the direction that is opposite to the direction of motion, like that. Let's denote that as F sub k. It's kinetic friction, friction that acts when there is motion between the block and the surface. Next thing to sketch or to label is the component of this 35 newtons, both along the plane and perpendicular to the plane. Along the plane, the weight has a value. Let's denote that as W parallel, and W parallel has a value of 35 sine 20 degrees, where the 20 degrees is the angle of inclination. Note that that weight also have a component perpendicular to the plane. Let's denote that as W parallel, and the value of W parallel is given by 35 cosine 20 degrees. Please refer to the videos on inclined planes to determine how we arrive at these results. Now we apply Newton's second law. Since the acceleration is up the plane, the net force must also be along that direction, following the direction of acceleration, because net force equals mass times acceleration. So let's determine the net force. There are only two forces acting along the plane. One is the kinetic friction, which is up the plane, and W parallel, which is down the plane. So the net force must be Fk minus W parallel, because Fk obviously must be greater than W parallel. Only then the acceleration will be up the plane. And that equals ma. Kinetic friction equals coefficient of kinetic friction, which is what we want to find, times the normal force, which is that, minus W parallel, which we know to be 35 sine 20 degrees. The mass is the weight, which is 35 newtons, over gravity, which is 9.81, times acceleration. We note that since the block is not moving up or down the plane, the normal force must be the same as W perpendicular, which is that. So mu k times 35 cosine 20 degrees minus 35 sine 20 degrees equals 35 over g times a. And this should give us the answer for mu k, because a is 0.7. So substituting 0.7 for a, we can solve for mu k, which will give you 0.44 for mu k. Let's look at another problem. Find the system's acceleration a, that is this, and the tension in the two chords, this tension and that tension, if given that the tension in the third chord is 70 newtons. Note that the surface of motion is frictionless. So you have three blocks connected by these three chords being pulled to the right with a force of 70 newtons. So the tension in the last chord is 70 newtons. So what would be the acceleration and the first two tensions? Let's begin with the free body diagram for object A. the forces that act on object A, the obvious one is the weight, and then you have this normal force from the floor on object A, let's call it N sub A, and then you have this tension T1 that's going to the right, there is no friction, and you must also label the acceleration, which is A. So let's write down F equals to ma for object A. There is only one force to the right that is acting on this object A, and that should supply the net force. So the net force on object A is quite simply tension T1, and net force equals mass times acceleration, so 10 times A. So that is equation 1 that we obtained from free body diagram of object A. Now let's look at the free body diagram of object B. As usual, they have the weight, which is 20 times gravity. You have the normal force acting on object B, which is N sub B. You have tension T2 pulling it rightward, and tension T1 try to pull it leftward. The acceleration of object B is A, the same as the acceleration of object A, because they are part of the same system. Now let's write down Newton's second law for object B. The net force on object B is given by T2 minus T1. The vertical forces will not contribute because the objects are not moving vertically. Because the acceleration is to the right, then it's obvious that T2 is greater than T1. And T2 minus T1 is the mass of object B, which is 20 kg, times the acceleration. So that is the second equation. Lastly, object C. Again, you have the weight, which is 30 g, normal force, and sub C, the tension T3 to the right, and tension T2 to the left. And object C have an acceleration to the right, A. The net force on object C is given by 70 minus T2. So 70 is T3. So 70 minus T2 equals the mass, which is 30 times acceleration. So that is equation 3. Let's proceed to determine the acceleration. Substituting T1 in equation 2, you get T2 in terms of acceleration to be 30a. And substituting T2 in here, you see you get 60a equals 70. And acceleration is 7/6 meter per second squared, which is about 1.17 meter per second squared. So that's your acceleration. Substituting A in equation 1, you get tension 1 to be 10 times 1.17, which is 11.7 newtons. So that's tension 1. Substituting A in this equation for tension 2, you get tension 2 equals 30 times acceleration, and acceleration being 1.17, and that's going to give you T2 to be 35.1 newtons. So there we go. We have acceleration, we have tension 1, 11.7 newtons, and tension 2 as 35.1 newtons. That solves the problem. Good problem. You have 3-link chain, so that is link 3, link 2, link 1 is lifted vertically like that with a constant acceleration of 3 meters per second squared. So that is the acceleration. Each link has a mass of 0.2 kg. Find the magnitudes of the force on link 1 from link 2. So force like that. And also the force on link 2 from link 3. So a force like that. Let's do part A first. So let's look at the first link. So that is the first link. What are the forces acting on this first link? You have its weight, which is 0.2 times gravity. And you have the force on link 1 from link 2, which is acting upward. Let's call it F. And of course you have acceleration A, which is known to be 3 meters per second squared. Now immediately you can write down Newton's second law. F minus 0.2g equals mass 0.2 times acceleration, which is 3. And that immediately gives you the value for F, which is the force on link 1 from link 2. And that's going to be 2.562 newtons. So that's part A. Let's look at part B. Now link 2, so that is link 2. What are the forces that is acting on link 2? So of course link 2 has its weight, which is 0.2 g. It has force from link 3, which is what we want to calculate. Let's label it as F3. In addition to that, it has the force from link 1 that is acting downward. Now this force on 2 from 1 must be the same as force on 1 from 2, which we have calculated in part A. So let's label that as F. And then you have the acceleration, which is A. So let's calculate the net force. The net force is upward because the acceleration is upward. So the net force is F3 minus F, which is downward. That is F. If you're wondering what F is the force on 2 by 1, which is the same as force on 1 by 2, minus the weight, which is 0.2 times g, equals m, which is 0.2 times acceleration, which we know to be 3. We have computed F from part A. It's 2.562 newtons. And putting everything together in this equation and recalling the fact that g is 9.81, you will be able to calculate F3, which is the force on link 2 from link 3. And that turns out to be F3 equals 5.124 newtons. And that is the answer for part B. And that solves the problem. Thank you for watching.